Hi geometry class, this is Mrs. Norden with your next lesson, and this is going to be a lesson on chapter 2 section 1. We're going to be using inductive reasoning to make conjectures. So we're going to learn about inductive reasoning a little bit and how to make conjectures. And then so here is our objective down here. We are using inductive reasoning to identify patterns and make conjectures, and then we're also going to find counterexamples to disprove conjectures. Our vocabulary in this section is right here. It says we're going to be learning about what is inductive reasoning, what is a conjecture, and how to find counterexamples. And what is a counterexample? All right, so our first thing that we're going to be looking at is identifying a pattern. In making conjectures, we first need to identify the pattern to make a conjecture. So here we have our first example where it says January, March, May. Notice it skips the months February and April. So after May, we're going to skip the month June and just go to July. So there we have it. We found a pattern, and we've made a conjecture that the next one in the pattern is July. You look at this second one. That's 7, 14, 21, 28. Those are all numbers that are multiples of 7. So if you look at the first one, that's 7 times 1, then 7 times 2, 7 times 3, 7 times 4. So the next thing in this pattern is 7 times 5, which is 35. Okay. All right, the last example I have for you on identifying a pattern is this one with triangles down here. We have a triangle. I'm going to call this triangle pointing up, and then pointing left, and then pointing down. Okay, if you notice something here, our triangle is rotating counterclockwise, and as it rotates, we see, like I said, it's pointing up, pointing to the left, down. So the next one in the pattern is that it is pointing to the right, and there is a triangle that's pointing to the right. So that's identifying patterns. Let's look at something else. So here are some definitions on what inductive reasoning is and what a conjecture is. It says, when several examples form a pattern and you assume the pattern will continue, you are implying inductive reasoning. Inductive reasoning is the process of reasoning that a rule or statement is true because specific cases are true. You may use inductive reasoning and draw a conclusion from the pattern. A statement you believe to be true based on inductive reasoning is called a conjecture. So the inductive reasoning that we're going to be using here is identifying patterns, and then from that, we're going to make a statement, which is called a conjecture. The statement that we're making is we're assuming this is true. And the next thing after that is showing that your conjecture is true for all cases and not just one specific case. And we will do that in our next examples here in just a second. All right, so making a conjecture says complete this conjecture. The sum of two positive numbers is, if you guessed positive, you are correct. So that's just making a conjecture right there, saying that the sum of two positive numbers is positive. That is a conjecture statement. So the next thing would be to prove that this statement is true. If you want to see a proof on this, I will gladly show you that in class. All right, the product of two odd numbers is, if you guessed odd, you are correct. And I'm actually going to show you how we're going to go about proving this for all cases and not just specific cases. Like a specific case would be, well, 3 times 3, those are two odd numbers, and that they multiply to be an odd number, because remember, product means multiplication. All right, let's try another one. How about 5 times 7? Those are two odd numbers that equal another odd number? Well, those are specific cases. That's not going to show that this conjecture is true for all cases. What is going to show that this is true for all cases is something like this. So I'm going to say let n equal this right here, 2x plus 1. Because this right here is an odd number. If you have an even value, 2x, any number times x is an even number. And then you add 1 to it, well, any even number plus 1, you end up having an odd number. So this statement right here, n equals 2x plus 1, that is showing that we have an odd number. And let's do another odd number because we need to multiply two odd numbers together to show that it is an odd number. Let's say m equals 2y plus 1. So another odd value. Now let's multiply these two things together. Let's multiply n times m, which is 2x plus 1 times 2y plus 1. Multiplying this together, if you haven't learned this yet, I'm using something called the foiling method, meaning first, outer, inner, last. That's how we're going to distribute all of our numbers to each other. We're going to do the first two numbers in our sets of parentheses, the outer two numbers in our set of parentheses, then the inner numbers, then the last ones. That's how you FOIL. So let's do the FOILing. First, end up giving me 2x times 2y, which is 4xy. The outer, 1 times 2x is 2x. 1 times 2y, it's 2y. 1 times 1 is 1. So if you notice something about these first three, we have 3 terms here that we can say all 3 of these have a factor of 2. So what we're going to do right now is something called factoring out a 2, or factoring out a greatest common factor. Or some teachers may call it reverse distributing, because that's kind of what we're doing. We're taking out instead of multiplying out. So if we take out a 2 from this first term, we end up with 2xy. If we take out a 2 from the second one, we end up with x. Take out a 2 from the third, we end up with a y. Okay. We've pretty much just proved our conjecture right here is true for all odd numbers. Because right here we have 2 times some number plus 1. So 2 times some number, that's even. That is even. Plus 1, which I told you before, even number plus 1 is odd. There you go. Our conjecture is true for all cases here. And that's how you would show a proof. If you want to go over this again in class, let me know, okay? All right, what I have for you on this slide is some stuff I've already stated a little bit. Like this first statement, it says to show that a conjecture is always true, you must prove it. Just like I did in that last example. I proved it for all cases, not just one specific case or several specific cases. Now the next statement says to show that a conjecture is false, you have to find only one example in which the conjecture is not true. This case is called the counterexample. So unlike proving something that is true, you have to show that all cases are true. For a counterexample, you just have to find one example that makes your conjecture false. So here's some ways that you can show that your conjectures are false. With a counterexample, you can use a drawing, a statement, or a number. Okay, so let's do some of it. But before we go on to that, here's some things that we've learned. In inductive reasoning, what we do first is look for a pattern. And then the second thing we do is make a conjecture. And then 3, prove it or disprove it. So prove it for everything, remember? And or give a counterexample, just one. That's all you have to give. So let's look for some counterexamples. It says show that the conjecture is false by finding a counterexample. So here I am telling you that these conjectures right here are false, and to find a counterexample. But let's look at something that I know that makes this conjecture actually true. Let's say let n equal 1. If we let n equal 1, then n cubed, which is equal to 1 cubed, or 1 times 1 times 1, which equals 1. This n cubed is still a positive number, meaning it's greater than 0. So this is true. This statement right here is true. But let's find a counterexample. So for integers, it doesn't just include positive numbers, it also includes negative numbers. So let's say let n equal -3. Then n cubed is equal to -3 cubed, which is -3 times -3 times -3, which is -27. This is less than 0, which is not a positive number. So this is our counterexample. N equals -3 is our counterexample. All right, so let's try one more. In this statement, it says 2 complementary angles are not congruent. Well, you could find many, many cases where this statement is true. So let's look at a case where this is true. Remember, complementary angles, they add up to 90 degrees. So one example that would be true is a 30-degree angle and a 60-degree angle. Those two angles are complementary angles and they are not congruent. So this statement holds true, but let's look at the one and only counterexample that would show that this statement or this conjecture is false, which would be this right here. If we had a 45-degree angle and another 45-degree angle, those numbers do add up to 90, so they're complementary. And that one and only example just that we do have, and it's the only case where it shows that this conjecture is false, but it doesn't matter. Just one case and one counterexample to show that this conjecture is false means this whole statement is false. Okay, so that is our counterexample for this one, and we are actually done. So we'll work on some more of these inductive reasoning and counterexamples in class whenever I see you next. So everybody have a good night. I'll see you later.